Okay, so I guess I'm going to start. And so this time I'm going to be talking about network security protocols and demystifying that. And so the purpose of this is a quick introduction into a somewhat scary field. I mean, it sounds like, oh my gosh, you know, I have to understand elliptic curves, you know, in order to do this stuff. No, the most important stuff are really basic system issues, and the world is not getting them right. And there needs to be more people with common sense, you know, that really understand, you know, things like how human beings work in order to make this stuff actually secure. So I'll describe the things that you need to know versus what you can trust other people to do. I'll describe some of the real problems associated with it. There's a talk title that I often give, especially at universities. The substance may change, but I really like the title, and it's How to Build an Insecure System Out of Perfectly Good Cryptography, which you might think, why does anyone care about that? But the world seems, you know, hell-bent to do it over and over and over. So I thought I would give people pointers on how to do that. But no, it's really quite amazing that people get so enthralled with the provable properties of some of the math functions and then kind of don't get the basic system things right. And this stuff is so incredibly important. The internet evolved in a world without predators. So, for instance, denial of service was just hand-waved away. You know, they said, oh, the security threats are unauthorized disclosure of information, theft of services maybe. But yeah, there's this other thing, denial of service, but we wouldn't have to worry about that because it makes no sense. You know, no one would gain anything from it. But it turns out that actually there is a thriving business in doing denial of service. Basically, you take over a whole bunch of machines that are owned by innocent people, but they haven't, you know, they haven't done the latest patches so you can break in. And then there's a couple of ways of making money with it. One is that you attack some site so that it keeps the merchant from their lifeblood, which is their customers, and then you get in contact with them and saying, hey, you know, if you pay me a certain amount of money, I can make it stop. And then the other way that you can make money from this is that you can offer your services for hire. So somehow, I'm not quite sure where you advertise this, but if you don't like your competitor, you can hire out you know, one of these networks of overtaken machines for a certain amount of time and pay a certain amount per hour in order to keep that website down for a while. But yeah, the world today is hostile. It only takes a tiny percentage to do a lot of damage, whereas most of the network protocols were designed back in the university, you know, collegiate sharing kinds of stuff, where people did not really worry about somebody actually trying to make the stuff not work. So it's important to be able to connect mutually distrustful organizations, and society is getting to depend on the internet more and more for reliability, not just sort of the traditional security concerns. A merchant can be caused to go bankrupt if you can keep their site down for a few days. So it's scary. Now, when you say, let's make things secure, you have to first answer, what do you mean by secure? And secure means different things to different people. So here's some examples of different things it could mean. It could mean that when you have a file, you want to limit disclosure of the contents of that file to only the set of recipients that you want to have access to it. Or it might mean that you want to monitor all communications in order to catch terrorists, which is, you know, like, not, you know, it's completely opposite of the first one, because in the first one, two terrorists may want to be able to talk without anyone listening in. You may want to be able to keep your data from being corrupted, or you may want to be able to destroy any computers that you think have pirated content on them. There was actually a bill proposed saying that if you, as a copyright holder, believe that somebody you know, has copyrighted stuff on their computer, you're allowed to do as much damage to their computer as you think that they stole in terms of copyrighted stuff, which I believe did not go anywhere, but that's kind of scary. You may want to be able to track down bad guys. So if somebody makes a threat or if somebody's a kidnapper, you want to be able to find out where these messages are coming from. Or you may want to be able to communicate anonymously so you can, do a whistleblowing thing and nobody can trace who it was that gave the information. So yes, Simpson Garfinkel gave a talk, and I thought this was a very cute observation. He was saying, the internet isn't insecure. It may be unsecure. Insecurity is a mental state. The users of the internet may be insecure, and perhaps rightfully so. So he's trying to get us to use the word unsecure instead of insecure. So now you also have to know what threat you're guarding against. So bad guys can eavesdrop. So how do you do that? Well, you can directly eavesdrop on a link, or you could compromise routers so that they store away the messages and send them to you. Or you could compromise the routing algorithm so that it can cause the data to go nearby where you are so that you can monitor it more easily. Or you can compromise DNS so that when somebody thinks they're talking to someone, you give them the wrong address so that you can peruse the stuff first and then pass the information to the real site so that someone won't know that you're actually doing this. You can also send arbitrary messages. A lot of people think that you can know where something came from by looking in the header and looking at the source address field in the IP header. And it's like, I can mail a letter to, the President of the United States saying that I am, somebody important. And just because I've put that into the return address on the envelope doesn't mean that I'm really them. You can replay recorded messages, which may or may not give you an advantage. If it turns out that at an ATM machine, you give it a certain number of bits and some money pops out of the drawer, it doesn't really matter whether you can decrypt what's going on. And you can write malicious code and trick people into running it. That probably dwarfs all of the other problems at the moment, but that's not primarily what this talk is about. But I get really annoyed at vendors for putting active content into everything. They think it's just so elegant to make everything be code. And I found out recently that fonts are programs. To me, a font would say, this is the shape of an A, this is the shape of a B, but instead, you can have user-defined fonts that say, oh, if you're displaying an A, run this code. What are they thinking? So basic terms, authentication is sort of, who are you? And authorization is, should you be doing that? And DOS is denial of service. Integrity protection is a kind of checksum that's put on data. Now, we're all familiar with like CRCs, which is a checksum put on data, but a cryptographic integrity check is one where unless you know the secret, you can't generate the integrity check, and in some cases you can't even verify whether it's right, but you won't be able to modify it, the data, without knowing the secret in order to, So some examples to motivate the problem. If you want to share a file between users, you put it out on some file store machine that's always accessible. The file store has to authenticate the users, because if you have a file there and you say only Radia is allowed to read it, then the file store has to know that I'm Radia when I contact it. So it has to know who's authorized to do what to the files, and it has to know who you are in order to enforce that access policy. Also, information has to be protected from disclosure and modification on the wire, or else eavesdroppers will also have the same rights to the data as I do. And users have to know that it's the genuine file store, or else, it isn't just the file store has to know it's me. I have to know I'm talking to the real file store, or else a bad guy can helpfully say, sure, send me your secret data. Electronic mail. You may want to be able to send private messages, so only the intended recipient can read it. You may want to be able to know for sure who sent a message. You may want non-repudiation, which means that when I receive a message from you, I know that it came from you, but I can also prove to somebody else that it came from you. So for instance, if you email me a purchase order, and then you want to back out of it later on, I can show to a judge, they really sent it to me. So if you send me a message with a shared secret that only you and I know, then I can know it came from you, but I can't prove to anyone else because I knew the same secret that you did in order to create the message, so I could create anything. And as I'll show you in a few slides, public key cryptography allows you to verify who it came from without being able to impersonate them. Anonymity is another thing that you may want to be able to do, is to send something where nobody can trace who it came from, which of course conflicts with knowing who sent the message. Electronic commerce, a lot of people think that the real problem is that you want to keep eavesdroppers from seeing your credit card. But actually, that's only a very small problem. If that were a problem, then you could never use your credit card because you use it at a gas station or a restaurant. There's all these minimum wage employees that if it were that important to steal individual credit card numbers, they could. But another interesting thing is you may actually want to hide your credit card number from a sleazy merchant. So you're willing to pay $25 or whatever the going rate is to get kiddie porn, but you know that the guy that you're buying it from is kind of sleazy, so you would prefer that he not see your credit card. You may want to be able to buy anonymously, so maybe you would like to not only hide your credit card from the merchant, but who you actually are. Or a merchant may want to be able to prove that I placed the order. So sometimes these goals conflict. Privacy conflicts with your company or the government wanting to be able to see what you're doing. So some companies want to be able to look over your shoulder and make sure you're not abusing resources by downloading porn. But they also might actually be genuinely trying to help you out by having spam filters and so forth. So if you really had end-to-end security, you couldn't have this virus scanning or spam filtering looking for what you're doing. If you want to make sure that you don't lose data that has been encrypted, then it's a good idea to give copies of your keys to lots of people. But then the more people that have the keys, so in case you lose the key, you can recover it, the more likely it is that one of those keys will fall into bad hands who will then look at your data. So it's kind of a trade-off. Denial of service versus preventing intrusion. You might say, well, if somebody guesses 3 bad passwords on an account, I will lock the account out. But then there's a denial of service opportunity that someone can purposely guess 3 bad passwords and the real user can't get in. So I'm going to demystify crypto. There's kind of 3 important kinds of functions. There's secret key cryptography, which is also known as symmetric key, because the sender and the receiver need to have the same magic number known as the key. There's public key, which is this magic thing that I'll get to, and cryptographic hashes. You use all these things for authentication, proving who you are, integrity protection, which is the ability to kind of protect the data so that only if you know the secret can you generate, can you sign the data properly, and encryption. Yes? Secret key is symmetric key because both sides have the same key, and public key is also known as asymmetric because there's kind of a different key for encrypting and decrypting. So, whoops, how about if we go forward? So with secret key cryptography, it's having 2 functions that are inverses of each other. And so intuitively, it's as if you're using multiplication and division, and everybody knows that division undoes multiplication. So if you and I share a secret, let's say 5, and you want to encrypt a message that I can read, you multiply the message by 5, and if I want to undo that, I divide by 5. Now, I'm not suggesting this is a good cryptographic algorithm, but you know, it's basically the same thing. There's some sort of horrible, complicated thing that's reversible. So there's a forward direction and a reverse direction. So there's a parameter known as the key. And even the person who designed the algorithm can't break it without knowing the key. So this is intuitively like knowing how safes work, but if you don't know the combination to that particular safe, you can't open the safe unless you have like lots of dynamite or something. Now, in theory, there's a lot of real paranoid people in the security community. In theory, you could design an algorithm that had what's known as a trapdoor, which is that even though you didn't know the key, you could somehow, break it. But these days, the accepted cryptographic algorithms are so widely scrutinized that nobody really believes that there's any sort of trapdoors in it. So ideally, every pair of users that want to talk will have a different shared secret. So in order to encrypt a message, it's some sort of function of the shared secret S and the plain text, which gives you the ciphertext, which is the encrypted stuff. To decrypt, it's a function of the same key S, and the ciphertext will give you the plain text. And authentication is somehow you're challenged to do something with your secret. So you're given a challenge and you send some sort of function of the secret and the challenge. An integrity check is some sort of function of the secret and the message, which gives you a checksum X. And to verify the integrity check, it's a function of the secret and the integrity check X and the message. So this is just an observation that I thought was really cute, which is, what I'm going to lead to is that the faster computers get, the more powerful cryptography gets, which intuitively makes no sense, because if the good guys get faster computers, so do the bad guys. But the only reason security is at all secure is because cryptography is secure is because it depends on the bad guy having only limited computational resources. Now you might think, well, but suppose the attacker really has a lot of computers. I mean, like a lot. Well, you can make the key kind of long enough that if every elementary particle in the universe were a Cray computer and it got to think for, 7 universe lifetimes and still wouldn't get through all the keys, well, no attacker is ever going to have that much resources. So you can brute force search the keys, but and that assumes that the computer will be able to recognize a potential plain text. So that is usually the case. There's some structure to the message so that you would be able to recognize it. A good cryptographic algorithm is linear for the good guys and exponential for the bad guys. What that means is that if you have a 100-bit key and you add 1 extra bit, it should only be 1% slower to do the operations like encrypt and decrypt where you know what the key is. But for the bad guy, when you add 1 extra bit, it doubles the amount of work to add 1 key because there's twice as many keys to brute force. So even 64 bits is pretty daunting to search through. The reason I choose 64 bits is that I knew somebody from a company who was so proud of his little device. He was doing a press conference, and he wanted to talk about how light it was, how many colors it came in, how many shapes it came in. And so when he mentioned that it had a 64-bit key, the press guy got all upset and said, 64 bits isn't enough, you could just guess the key. And the guy said, no, 64 bits. And he didn't realize how confused the press guy was. So as he was talking about all these other wonderful things, the press guy kept asking questions. How many is that? And he said, 2 to the power 64. And then later on, the press guy said, is that more than 1 million? And he said, yes. And so the article came out that this device, had more than 1 million possible different keys, and the poor engineer was. But at any rate, so now if you believe that you can come up with an algorithm that's linear for the good guys and exponential for the bad guys, if you were working with a 100-bit key and the performance was adequate for doing encrypt and decrypt and all that, and then you got a computer that was twice as fast, now you could start working with a 200-bit key and have the same performance as before. Now the bad guy also gets a computer 2 times as fast, but his work factor isn't twice as much as it was before. It's now 2 to the 100 times as much, which is more than 1 million. So now the next kind of cryptography is known as public key crypto. And it is just amazing to me that anybody thought this could possibly be done. And it was very interesting that the way that it came about was first they said, wouldn't it be cool if we could invent a kind of math that had these properties? Now, if you look at these properties, it's absurd. I mean, what were they smoking when they thought that it could have these properties? But indeed, a few years later, people did come up with something that had these properties. So the idea is public key cryptography is kind of analogous to having nobody ever invented division. They only know how to do multiplication. And each user comes up with a pair of numbers, and the numbers are inverses of each other. So I might come up with the pair of numbers 5 and 1/5, and I tell everybody 5, and I don't tell you 1/5. And so now if you want to encrypt a message for Radia, you multiply it by 5, and if I want to undo that, I multiply by the inverse number, 1/5, and I get the original thing back. So you have two numbers, E for the public key and D for the private key, and they're inverses. Now, in our book, which we kind of wrote when this stuff was, the first edition, the second edition is very recent, but the first edition we wrote when, the terminology was still very murky and stuff. We decided to call it public key and private key to differentiate it from like a secret key, which is the shared thing. And then when we needed a letter for public key and a letter for private key, we discovered that we couldn't use P for both without making the reader confused. So we use E for public key because that stands for encrypt, and D for private key because that stands for decrypt, even though they're really just inverse numbers. So it's quite magic. Why is it that I can tell everybody E and you can't figure out D? Why can't you figure out the inverse number? So I just say, oh, well, the mathematicians have come up with something where I can tell you one number and you can't figure out the other one. And so then you feel good for like 2 seconds until you say, wait a minute, how did you get the two numbers if you can't derive one from the other? And so indeed, it is like really cool. It is actually quite easy to explain. It takes about 15 minutes to explain how RSA works, but we don't quite have 15 minutes here. So. But I do in the halls if anyone wants to hear about it. So one of the best features of public key cryptography is the notion of a digital signature. It's an integrity check that's calculated as a function of your private number and the data. And other people can verify it. Now this seems kind of weird. It's just a number. If you can verify that this is the right signature, why can't you forge somebody's signature? And the answer is the numbers are so big that there's no way to do it without just brute force trying lots of numbers, and there's just too many numbers to try. So with digital signatures with public key, I can sign a message that anyone can verify without being able to impersonate me, whereas with secret key, the verifier needs to know the same secret. So that's one of the reasons public key is so much more powerful. Now, I did in the description say that I would teach you enough crypto to impress a date. And so I will tell you the secret key and the cryptographic message digest or hash algorithms just look like a messy way to mangle bits. It reminds me of, somebody locked a bunch of mathematicians in a room with way too much beer and way too much time, and they just kind of got sillier and sillier and said, oh, how about if we swap these bytes, how if we multiply by this? And it doesn't look like there's any logic to it whatsoever. But the public key algorithms are actually quite understandable. So what they do is they pick some math problem that people assume is hard. Why do they assume it's hard? Well, because mathematicians have been thinking about it for thousands of years and haven't come up with a good solution, so we hope it's hard. Somebody could solve it tomorrow, in which case we'd be all upset. But we're hoping they won't. So I'll explain Diffie-Hellman, which is this wonderful protocol which is quite easy to understand. So what this protocol is where I have never met you before, or I don't know whether I have or not, because I'm bad at it, but let's say I've never met you before, and the only way that I can talk to you is communicating across this crowded room full of nefarious characters. And you and I need to know a secret so that we can send like encrypted data. And so what this Diffie-Hellman protocol allows us to do is, despite the fact that we have no way of communicating in private at all, we can only talk where everyone else hears me, I am going to send you a message that everybody else in the room will hear. You will send me a message that everybody else in the room will hear. And at the end of these two messages, you and I will know a secret that nobody else knows. Isn't that astonishing? And so basically the way that it works is it's based on this problem. So we're assuming the following problem is hard because we don't know how to do it. So the problem is that if you know G and p, you know parameters g and p, and you know what g to the x mod p is. What's x? So what number did I have to raise g to mod p in order to get this? Where modular arithmetic is the answer is always an integer between 0 and 1 minus the modulus. So you do ordinary arithmetic, then you divide by the modulus and get the remainder. So let's take my word for it that we assume this thing is hard. So we don't know what we needed to raise g to mod p to get this thing. So you could plug numbers in. Suppose you raise g to the 17 mod p. Nope, that's not it. And you could go through the numbers. So this is the Diffie-Hellman protocol. Alice and Bob agree on G and P. And so if we didn't agree before, if it isn't like in the protocol where we always use a certain number for G and always use a certain number for P, I can tell you, let's use 7 for G and let's use this, huge prime number for P. So everyone in the room and you and I know what G and P is. Alice and Bob each choose a random number. So Alice chooses A, Bob chooses B. Alice sends g to the a mod p to Bob. Bob sends g to the b mod p to Alice. Now Bob takes what he got from Alice and raises it to his secret number, b. If you raise g to the a to the b, and you remember 11th grade arithmetic, the exponents multiply, so you get g to the a times b. And likewise, Alice takes what she got from Bob, raises it to her secret number, and g to the b times a, she'll also get g to the ab. So they'll agree on g to the ab, and nobody else who saw these two messages can do it because, well, we don't know how. So we assume that they can't. So that's what the Diffie-Hellman protocol is. Now, there's a problem with it, which is known as the man-in-the-middle attack, which was kind of cool because our publisher, who goes and reads through there to make sure that you're not saying anything offensive, said, can you come up with some gender-neutral term for that? And so we briefly talked to each other and said, should we call it person in the middle? And it's like, no. So we at least made the person in the middle female. So it's Trudy, which stands for intruder. So here's a man in the middle attack. The problem with Diffie-Hellman is that although you and I can establish a secret, I don't really know who I'm talking to. So let's say that Trudy is some malicious code sitting on a router between Alice and Bob. So Alice sends a message to Bob saying, I want to use g to the a mod p. Trudy does not forward that. Instead, she sends g to the t mod p where she knows what t is. Bob says, let's use g to the b mod p. Trudy again does not forward that, but sends g to the t mod p. So now Alice and Trudy agree on a secret g to the at, and Trudy and Bob agree on g to the tb. And now Alice thinks that she has secure communication to Bob. And so she can check. She can say, is that really you, Bob? But whatever she says gets decrypted by Trudy and re-encrypted. She can say, just to make sure it's really you, what cafe did we meet at in Paris, and so forth. So how do you solve that problem? Well, what you can do is signing your Diffie-Hellman numbers with your RSA key. So assuming that both Alice and Bob have a private RSA key and know the other one's public RSA key, then you not only send g to the a mod p, but you sign it. And then you verify the signature before you use it. And that way you can be guaranteed that there's no man in the middle. So this is fine, except after you think about it for a minute, you go, excuse me, if we already know RSA keys for the other side, why are we fooling with Diffie-Hellman? And the answer for that is this property known as perfect forward secrecy, which is that you would like to have a conversation such that if after the conversation you throw away A and B and G to the AB, nobody can subsequently decrypt the conversation, even if they recorded the entire conversation and then steal all of your secrets. So, whether or not that's an important property, I'm telling you that because that's basically how IPsec works. It's a signed Diffie-Hellman kind of thing. So an example of a protocol without perfect forward secrecy is SSL, where the client picks a secret, sends it to the server, encrypted in the server's public key, and then the rest of the conversation is protected with that secret. So if somebody subsequently steals the server's private key, they could decrypt the whole conversation. Because if they can decrypt the first message, it will tell them the secret with which the rest of it is protected. So now, cryptographic hashes is kind of the third piece in the puzzle. This was invented because the guys who invented RSA, which is this really nice public key algorithm, people said, oh yeah, that's very cute, but who cares? Because it's so slow, it's like 2 or 3 orders of magnitude slower than traditional secret key encryption. No one would be able to take a message like war and peace if you wanted to digitally sign that. You just wouldn't be able to sign that with public key. And that's the whole idea of public key. You want to be able to sign messages of arbitrary length. And you also wouldn't be able to encrypt with it. So basically, in order to sign a large message, they came up with this notion of, wouldn't it be nice if we could come up with a mathematical algorithm known as a cryptographic hash, such that you can very quickly come up with a fixed size number of bits, like 128 bits, that represent the message. And then you can sign that, and it will be as good as signing the message. So this depends on the fact that nobody will ever find 2 messages with the same digest, because when you sign a digest of a message, you are implicitly signing any message that has the same digest. Now the problem is, how many 128-bit digests are there? There's 2 to the 128. How many messages are there of arbitrary size? Well, unlimited. So therefore, there's gazillions of messages that all have the same digest. But we're just kind of assuming that with 128 bits, it's so unlikely you would ever actually find 2 with the same, that you'd ever stumble on 2, and that you construct these messages, these digests, such that it's impossible to kind of say, I have a message and I want the digest to be this. So if I change these bits, I can make it a little bit smaller. And no, every time you change a single bit in the message, it's as if you flipped 128 new coins to come up with a totally new random number. So, popular secret key algorithms, there's DES, which was the old standard, which had a 56-bit key, which is not big enough. You can, the EFF demonstrated that they built a machine for not very much money that could go through and brute force search DES keys in a matter of a day or 2. There's triple DES, which fixed the key size by doing DES 3 times, but it makes it 3 times as slow. RC4 is a popular algorithm. It's very cute. It has a variable length key. It's what's called a stream cipher, where you and I, with the same secret key, generate a pseudo-random stream of bits. And then the way that we encrypt a message is I take the pseudo-random stream of bits and do an exclusive OR of the message with those bits. And then for you to undo that, you exclusive OR with the same bits, because you and I are generating the same stream of bits. AES is a replacement for DES, and it will probably take over. AES stands for Advanced Encryption Standard. It was kind of chosen by NIST, which is a branch of the U.S. government. They genuinely wanted the world to have a better algorithm. So it was at least as interesting a public relations problem as a technical problem, because there were like so many years of bad blood between the government and industry where they were trying to do everything possible to hinder deployment of security, and then to have the U.S. government step up and say, we're here from the government and we want you to have better crypto. Here's a wonderful algorithm that our pals in the NSA invented. Why don't you all use it? Now, indeed, it could have been a really fabulous algorithm, but people would have a hard time accepting it because they'd be really paranoid there would be a trap door or something. So the one strategy NIST could have used was waiting for a few years and see if it would happen by itself. And they tried it, and that didn't happen. So the next thing they did was they decided to have an international competition where anybody could submit proposals, and then and your proposals had to be like very open about exactly how you went through the design, and you had to not enforce patents against it and stuff. And then every year they had a conference where they had all these highly motivated cryptographers who wanted their thing chosen, given a chance to poke any holes they could at the others. And meanwhile, NIST went and built all the algorithms to show, to compare them with performance, you know, how many gates it took, how much power, and so forth. And ultimately, they took this thing called Rijndael, which was done by 2 Belgians, and it's very cute, and that's known as Advanced Encryption Standard. Popular public key algorithms, there's RSA, which has a very nice feature, which you can make the public key operations very fast, but the private key operations will be slow. We know what the patent situation is on RSA, which is that the patent expired. There's another thing called elliptic curves, which is the claim is that it can be just as secure with much smaller keys, so therefore it would be obviously much more efficient. Why isn't it taking over the world? I mean, by all logic, it should if the performance is better. But for one thing, the public key operations may still actually be better with RSA because you can do this trick of making public key very fast. And public key, one of the things you would do is verify a signature. So if you think of signing a document once, but thousands of people have to verify the signature, that's a very nice property for RSA. Whereas elliptic curves, the encrypt and decrypt are going to be the same performance. But some people are worried about whether there's patents associated with ECC, which is, I think, why it hasn't taken over the world. Okay, so hash stuff. The most popular hash today is SHA-1, which was done by the government. Older ones are still around, but they're, quote, broken, unquote. Now, a popular secret key integrity check is to take the data, concatenate it, combine it with the secret, and do a hash of it. This particular use of secret key, hashes, none of the hash algorithms that are broken have any weakness when you're doing this. So when something is broken, it's not clear that it really matters for your particular application. But what broken means is that they were able to come up with something where they could come up with pairs of messages that had the same digest, or that they can't really do it, but instead of having it be 2 to the 80 operations, in theory, they can instead do it in 2 to the 69 operations, which is not that exciting. So the real problem with this thing being broken is what I call the New York Times attack, which is that it doesn't, your system is perfectly secure, but once there's a New York Times story about how this particular component is broken, then your customer will say, hey, wait a minute, why are you trying to sell us this garbage that's using this component that's broken? And you can go through and try to explain the subtle security reasons why it's not broken in the context in which you use it. But that's like way more work than just using something that the New York Times has not declared broken. So, right. So how do you encrypt a message? You don't want to encrypt anything with somebody's public key. That would just be too slow. So the way that it's done is you take a message and encrypt it with a secret key, because secret key cryptography is 2 or 3 orders of magnitude faster. So it's fine to encrypt a message with some secret key K, but Alice won't be able to read it because she doesn't know what K is. So in order to give Alice the message, you have to not only encrypt the message with K, but you have to tell Alice what K is. And the way you do that is you also send Alice K encrypted with her public key. Now, if you're going to encrypt something with the public key, why not just encrypt the message? And the answer is that the message is big. The key is small. So it's not a performance problem to encrypt the key. For signing things, instead of signing War and Peace with Bob's private key, you take a digest of the message, sign that with Bob's private key, and you send the message and this digest. Now, how does Alice actually know that this is the right thing? What she has to do is reverse this using Bob's public key to get what Bob claims is the digest, and she has to independently compute the digest and see if she gets the same number, and if she does, then she verifies it. And you can do both at the same time. You can sign and encrypt something. So yeah, don't try this at home, meaning don't invent your own crypto algorithms. There's no reason to do this except for the Cryptography Guild. Even if you could invent a better one, which, what does better mean? It's faster, it's more secure, no one's going to believe it. So just, you know, it's not worth your time to do it. So it's better to have a well-known, well-reviewed standard. So how do you authenticate? Let's say that Alice and Bob both share a secret key K. So Alice says, I'm Alice, and Bob says, oh yeah, if you're Alice, Bob picks a random number R and encrypts it using their shared secret and says, if you're Alice, what number was I thinking of? And if she can decrypt it and tell you R, then you know that she must know the same secret that you do. Now, in the olden times, people did authentication across a network without cryptography. And by olden times, I mean today. You know, one way is with passwords, where you just transmit the password. Another is based on addresses, by looking at the IP source address. So in the book, this is a quote from our security book, which sort of explains the real problem behind all this. Humans are incapable of securely storing high-quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They're also large, expensive to maintain, difficult to manage, and they pollute the environment. It's astonishing that these devices continue to be manufactured and deployed, but they are sufficiently pervasive that we must design our protocols around their limitations. So how do you authenticate people? Well, you know, people say that there's kind of three ways of doing it. One is what you know, so it's something that you can remember, like your mother's maiden name or a password. Another is what you have, like a front door key. And a third thing is what you are, like biometrics. Now, people say that it's nice to have two-factor authentication, because if you lose your front door key and somebody steals it, they can get in. But if there's also a password associated with it, then you can make it more difficult for somebody to impersonate you. So that's known as two-factor authentication. I was once at a marketing presentation by somebody, and it just drove me crazy, because he kept talking about how their thing was two-factor because it required two passwords. So passwords, you know, are subject to eavesdropping, and they're also subject to online guessing and offline guessing. So let me explain the difference between online guessing and offline. Online guessing, if the only way to guess a password is where the system can monitor how many times you're doing it and make it slow, and possibly, like if it's in the military, shoot you if you guess wrong too many times, then you don't need a very good password. But if instead you can do an offline attack where you can listen and then have some number that you can go take down to your bank of Cray computers in your basement and test lots and lots of passwords, then you need a lot more secure of a password to withstand that. So here's an example of where a system would allow you to do that. A lot of protocols in use today, the shared secret between A and B is configured as a password that people can remember and type in. So Alice, who knows her password, walks up to a workstation, says, my name is Alice, this is my password. The server knows some sort of function of the password. The workstation computes the function of the password, and this is the shared secret that the workstation and the server knows. It's based on the password. So the workstation says, I'm Alice. The server sends a challenge, and then the workstation sends back some function of the challenge and the password. So if you were to eavesdrop on this, you could say, if her secret was fiddlesticks, is this what she would have answered to that challenge? And you could go through a whole dictionary of 50,000 or so possible passwords that people might use. Okay, so now I'm going to talk about some cryptographic handshakes and just sort of interesting issues to think about when you're designing these. So, just to make sure, I'm supposed to end at 5, right? Okay, all right. So, Alice says, I'm Alice. Bob sends a challenge, and she encrypts the challenge with their shared secret. Another thing that people tend to do is to say, I'm Alice, and just send the time of day and encrypt that with the shared secret. So this is nice. It's only one message rather than three, which isn't that exciting, except because three messages rather than one. But there's a lot of protocols out there that expect you to send a password. And here, you don't have to redesign the protocol. You could replace the password with the encrypted timestamp, and you don't have to think about how to redo the protocol to have more messages. So that's kind of a nice thing. But when you do this, you have to be real careful that someone can't replay it, because times are going to be a little off at the source and destination. So the receiver has to be reasonably forgiving. If the time is within 10 minutes, you'll say, okay, it's close enough. But then you don't want someone to be able to impersonate Alice for the next 10 minutes by taking what they saw and sending it. So therefore, what you have to do is Bob has to remember all of the timestamps from Alice that were successfully used within the last 10 minutes. When it's older than 10 minutes, you can throw it away because you would not have accepted it because it was too old. But when it's within that time. So like one example of a system that I saw that got it wrong was that they had this, they did it the right way, but then they said, let's make Bob be a whole bank of servers. And so when you ask to talk to one of these things, your query is routed to one of these things at random. And they didn't have the servers share their, synchronize their database of which things were used. So with high probability, your next query would go to a different server, and you would be able to be authenticated. Here's an interesting problem. Alice says, I'm Alice. Bob says, here's a challenge. And Alice does something with her private key, either signing it or decrypting it, because that's kind of what you do with private keys. So this is a perfectly secure protocol for authentication, but when you take a step back and look at the whole system, it might be really dangerous, because how does Alice know what she's signing? This might be a totally random 128-bit number, or it might be a message digest of a message saying, I agree to pay Bob $1 million. So how do you know what you're actually signing when you're putting, so you have to, kind of pad the message in various ways so that you can't get tricked. One of the things cryptographers sometimes say is don't ever use the same secret in multiple ways. And that's just not very realistic, because you'd need to have, too many different keys. Okay, I think I'm not going to bother with Lamport's hash, though it's really cute. So another instance of a handshake, where just to show that handshakes can be done wrong, is Alice says she's Alice. Bob gives her a challenge. She encrypts the challenge. And then Alice says, here's a challenge, and Bob encrypts the challenge. So this is mutual authentication, which there's nothing really wrong with this, except that if you have any soul as a protocol designer, you'll realize that it doesn't need to take that many messages. You can do it in fewer messages. So one thing, you could certainly combine these two messages. But if you're clever, you can do it in 3 messages. So you can do it in 3 messages by saying, I'm Alice, here's my challenge. Bob says the answer to that challenge, gives his own challenge, and Alice encrypts that challenge. And now they've done mutual authentication in 3 messages. Well, what's the problem with that? The problem with that is known as the reflection attack. And let me show you. So Trudy says, I'm Alice, because Trudy doesn't know the secret, but she's trying to impersonate Alice. So she says, I'm Alice, my challenge is R2. Bob says, here's the answer to R2, and here's your challenge, R1. And now Trudy is stuck because she doesn't know the answer to R1. But what Trudy does is she starts a second parallel connection and says to Bob, I'm Alice, my challenge is R1. Bob helpfully tells her the answer, and now she can complete the first one. So there's various ways around this. You can make sure that you use a different secret in the 2 directions, or you can make sure that the initiator chooses even challenges and the other one odd challenges, or you can encrypt your name in with it or something. But you have to kind of be aware of these kinds of attacks. Okay, so now secret keys. How do you manage to share a secret with everyone that you ever might want to talk to? Well, you could configure n-squared keys, just in case you want to talk to this, nice family in Kansas. But, that would be a real pain. So instead, the way that the world, has decided to do it is with a magic box known as a Key Distribution Center, or a KDC. In Microsoft terms, it's called a domain controller. But it's a magic box that knows a secret for each user, and each user only needs to know one secret, which is the secret that they share with the KDC. And this is basically how Kerberos works. So the KDC knows that Alice's secret is K sub A, and Alice knows that her secret is K sub A. And this is great. Everyone can now talk to the KDC, but who cares? Who wants to talk to the KDC? Really, Alice wants to talk to Bob. And the way when Alice wants to talk to Bob, she asks the KDC to introduce them. And so the way that works is Alice says to the KDC, Alice wants to talk to Bob. The KDC randomly chooses a new secret, K sub AB, sends a message to Alice, which it can do securely because it knows a secret for Alice, saying, if you want to talk to Bob, use K sub AB, and can send a message to Bob saying, if you want to talk to Alice, use K sub AB. And then they can talk to each other because they now share a secret. Now, who is going to be the KDC for the entire world? Who are you going to trust to know all secrets for all users? So Kerberos does not scale for a couple reasons. One is the database would be too large to manage, but more importantly, there's only a certain limit to how much trust scales. So only within an organization, or maybe only within a department of an organization. So the term realm is the set of users of a particular KDC. So it's sort of all the secrets associated with one KDC database is that KDC realm. You can do cross-realm authentication. Alice at realm A can talk to Bob at realm B, provided that there's some sort of trust relationship between those KDCs. So that they're willing to set up each other's users, or if you can find like a whole path. So yeah, there's some way of perhaps doing that. And I'll talk about kind of how you would build these hierarchies when I talk about public key. But for now, don't worry about hierarchy. So the next way of doing key distribution is with public keys. So the way to do, sometimes when people see public key cryptography, they say, oh good, we've solved the key distribution problem, because the keys don't need to be kept secret. Instead, you can just take out a billboard saying Radia's public key is 75. And, but the problem is, how do you know that it was really me that put that billboard out? If somebody could trick you into thinking that my public key is something that they know the private key for, then they could forge my signature to you. Or they could cause you to encrypt a message that they'll be able to read and I won't be able to read. So therefore, unless you have some really secure mapping between my name and my key, all the fancy math in the world is doing you no good. So you have as much of a security problem with public keys, which is you need a secure bonding between the name and the key. And the way the world, kind of knows how to do this is that there's a trusted party known as the CA, for Certification Authority, that signs a message known as a certificate. And the certificate is a signed message that says, I vouch for the fact that this number is Radia's public key. So now, if everybody has their key certified by the CA, and they know their own private key, and they know the CA's public key, they can authenticate. Now, each one of these things is not so simple. How do you get certified? How does it know it's really you? How do you know your private key, given that humans can't securely store, cryptographic keys? How do you know the CA's public key? But, for now, let's just assume that somehow everybody knows the CA's public key, they know their own private key, and then the way that you can talk is that Alice can immediately start talking to Bob. She doesn't have to talk to a KDC first. She can say, here's my certificate. Bob, knowing the CA's public key, can verify the signature, now knows Alice's name and her key. Likewise, he can send his certificate to Alice, and now they can do authentication and encryption and all that. So now I'm going to give you a functional comparison of basing the world on secret keys, like you would with Kerberos, versus basing it on public keys, like you would if you, were using a PKI-based system. PKI stands for Public Key Infrastructure. The KDC solution is less secure because you have this box that has a highly sensitive database of all user secrets. It has to be online and accessible via the net, or else nobody can get any work done. So it's going to be a complex system because it has to have a whole network stack able to talk simultaneously to lots of users. Therefore, it will probably have exploitable bugs, and it will be an attractive target for people to probe and look for any sort of bugs. And if they get in, they've hit the jackpot because it has all user secrets there. It has to be replicated for performance and availability because if it's ever down, you can't talk. And any replica that you had physical access to, you now have this highly sensitive database. The KDC solution is going to be more expensive because it's a big, complex, performance-sensitive, replicated box, whereas the CA is just a glorified calculator. It just, when you hire a new employee, like you make them a badge, it would be okay if it took a couple minutes to make this certificate. It can be offline and locked in a vault and just taken out once a week in order to create the new user accounts for the new employees. Performance, the math in public key is slower, but I believe that would be dwarfed by the necessity to talk to a third party before you can talk to Bob. CAs probably work better between realms. What I mean by that is I work at Sun. If I were to, so I'm at a big company behind a firewall. If I want to talk to you and you're at Microsoft, you're also at a big company behind a firewall. And so it's unlikely that the Sun IT department is going to open a hole in the firewall for outsiders to talk to the most security-sensitive box in our net, which is the KDC, in order to do cross-realm authentication. Whereas if you're doing public key stuff, I can just email my certificate and we can manage to talk securely. Now, revocation levels the playing field somewhat, but let's not worry about this. Now, given this, why did the Kerberos people do it on secret key? You know, were they like stupid? Did they not understand public key? And the answer is they had no choice at the time because the licensing fees on RSA were just prohibitive. So they had to design a system that avoided all use of public key. But these days, we don't have to avoid that. So I'm really hoping the world will migrate to using public key stuff because it's so much better in so many different ways. Yes, yeah, right. Kerberos is kind of migrating to public keys in various ways, but it still has kind of the thing that you talk to this third party, which would be nice to get rid of. Okay, yeah. So I talked a little bit about revocation, but that's not so interesting, and I'm worried about time. So this I'm really passionate about. So I'm going to talk about strategies for building a PKI. So these will become much more understandable when I go through them. So the monopoly model is, who is the CA going to be? So in the monopoly model, what you do is you choose one organization universally trusted by all organizations, all countries, all companies, whatever, and you embed their public key in absolutely everything. Every piece of software, every hardware knows that public key, and everyone has to get certificates from this one organization. Now that's nice and easy to understand and to implement, but what's wrong with that? Well, one is monopoly pricing. The more widely deployed something is, knowing one key, the harder it ever is to migrate away. So, you know, if that monopolist is clever, they'll give it away like crack first to get the whole, world, hooked on it, and then kind of gradually raise the price. And if they're careful never to raise it too much at any one shot, the world will just shrug their shoulders. And it's very, very important when designing these things not to design a monopoly in there. And the world has blown it on things like the DNS namespace and so forth, where they've built in a monopoly, and then surprise, when that organization starts charging too much, and the world says, we'd like to let other guys be in competition with you, or we'd like to award it to someone else, they go, no. So, you have to kind of think about that beforehand and not build in a monopoly. Getting a certificate from a remote organization will be insecure or expensive, or both. And, all right. That key can never be changed. And it's just good security hygiene to change keys occasionally, just like it's a good idea to change the keys on your front door. Even though you don't remember loaning your key to someone bad, it could be that you left it on the counter someplace and someone made a copy. Also, it could be that cryptography has progressed such that you would like to use different keys or like to change to a different algorithm. And so building it in where you can never change that key is not a good idea. Also, the security of the world depends on that one organization never having a corrupt or incompetent employee that can be tricked or bribed or threatened into misusing the key. So the next model I'll talk about is what's in browsers, and I call it the oligarchy model, which is that they come configured with 80 or so trusted public keys, and your browser will accept a certificate from any of those, signed by any of those 80 organizations. Usually you're allowed to add or delete from that set. So, you know, like Netscape could say, well, it doesn't really matter what keys I put in that set. If you don't trust them, you're welcome to change this default set. It does eliminate monopoly pricing, but what's the problem? Well, now it's less secure, because before the security of the world depended on one organization not having an employee that you could attack, that you could compromise. Now you have 80 organizations, and if you can compromise an employee at any one of them, then you can be in trouble. There's a quote that we have there. One of the co-authors was at a meeting once where there was a bunch of security people talking about, oh, but what if that was compromised? You know, what about this? And finally there was a management guy there that couldn't stand it any longer, and he finally kind of pounded his fist and he said, you security types always talk about compromise as if it's a bad thing. Good engineering always involves compromise. So anyway, a naive user also can be tricked into using a platform with bogus keys, because you think, am I safe doing banking at this airport kiosk? Why, yes, they're using SSL, which is a fine protocol, and they're using 128-bit crypto. Nobody's ever going to break that. But the problem is, how do you know that a previous user didn't diddle with that set and add, you know, totally bizarre CAs in there? Also, although it's not a monopoly, it still favors certain organizations. Why should who are these 80 organizations? You'd kind of like to believe that the browser vendor went to great efforts to visit them all and decide on, you know, their policies and procedures and all that before putting them in. But no, you pay them $100,000 and they put your key in there. Okay, the next model I call the anarchy model, and this is what's in PGP. The idea is that anyone can sign a certificate for anyone else. So what it is that no one tells you who to trust, but you've met some people and you can trust them because they look nice, and they give you their public key on a business card, and you configure your workstation to know their public keys. And every time you have a gathering of nerds, like an IETF meeting, and I'm not sure whether they do it at NANOG, they have this thing called a PGP key signing party with some sort of ritual in which you say who you are and what your keys are, and anyone who comes to this party can certify anybody else. And then there's these public databases. I know there's one at MIT where anyone can donate certificates to. So the idea is, if I want Gwendolyn Smith's key, I want to send her an encrypted message. If my workstation doesn't have Gwendolyn Smith in there because I haven't gotten her business card, I then look at MIT's database and see if I can piece together a path from one of my trust anchors, which is one of the things I've configured, to the name Gwendolyn Smith. So now what's wrong with this model? Well, it's not going to scale. Think about how big these databases are going to be if you used it on an internet scale. If you have 1 billion users, each user signs 10 certificates, that's a huge database. And even if by some miracle you could find a path from a key you know to the name that you want, how do you know whether to trust that path? So in a small community where everyone's just honest, it works okay. But once there's bad guys willing to poison the database, you know, there's all bets are off. So, you know, like my favorite, I mean, so what undoubtedly your browser would do is show you all the links in the chain and make you as a human decide whether you can trust Dwight Edwards from, you know, Idaho to certify, you know, Jim Smith's key. It's like, how can a user make such decisions? So, you know, like one example is Mother Teresa says that this is Charles Manson's key. That's like, Nothing wrong with that. I'm sure she's very careful when she checks certificates and all that. But then should you trust the next link in the chain where Charles Manson says that this is George Bush's kid? And you know, some of you are too young to know that Charles Manson was actually not a good guy. So now I'm going to tell you the model that I wish the world would use. So one important thing is that trust should not be binary. It shouldn't be, is this CA trusted? But instead, a CA should only be trusted for certain certificates. And the only policy that I've ever seen that makes any sense to me whatsoever is that it's based on names. Because how else do you know which users someone should be certified by? So it makes sense that the name by which I know you implies who I trust to certify your key. So if you know me as, you know, radia.perlman.sun.com, you would trust Sun to certify my key. If you know me as roadrunner.aol.com, you'd trust AOL to certify the key of that name. So one way that people think of making this work is what I call top-down, where everybody knows the root key. And, oh, you have a hierarchical namespace, which actually we have with DNS, where each node in the hierarchy is represented by a CA, and the parent node, like sun.com, certifies the child node, like laboratory.sun.com or sun.com.labs or whatever. And so that makes it very nice. You know exactly what chain to follow. You don't have to explore like you would with PGP. But you still have a monopoly at the top. So to get rid of the monopoly, I call it the bottom-up model, where you still have the hierarchical namespace, but instead of just having the parent certify the child, you also have the child certify the parent. And if you have links in both directions, you can start any place. You don't have to start at the root. You can start with your own key. So in order to certify, and the most elegant place to start is with your own key. So you have, you know, your own private public key on a smart card. If Alice wants to get to Bob's key, she has to go up to the least common ancestor and then down again. To get to Carol, she has to go up 2 levels and down. Now, it's also nice to have cross-links. So instead of waiting for the whole PKI of the world to get connected, you can build a little PKI in this organization, a little PKI in that organization, and if they cross-certify each other's keys, then the rule is that you start wherever you do, you go up until you get to a cross-link that gives you access to an ancestor of the target name, and then you go down. Or until you get to a least common ancestor, and you go down. So, but the rule, and if you can follow a cross-link, it seems like you're back to the PGP model, but no, you only follow a cross-link if it yields an ancestor of the target name. So you don't go to a cross-link to IBM in case IBM knows HP's key. You only follow the cross-link if it gets you into that namespace. Now, after a while, there is a business case to be made for offering root service. So you say, if you get tired of managing thousands of cross-links, I offer inter-organizational certification. And if you hook into me, this is how much I charge and so forth. And you'll automatically be connected to the following 300 organizations. So here, it might seem if there were a root that managed to become the most popular root and had thousands of organizations, you might think it would be a disaster if that key were compromised, but no, or if you wanted to switch it out. Me as a user, way down in the depths of Sun, I don't care who the inter-organizational thing is. If that were to change, Sun has to revoke the old key and put in the new key, but it doesn't affect me as a user. The only time it affects me as a user is when the CA in my building, that, you know, the person that gave me the badge and certified my key originally, if that changes, then I have to do something magic. But then there's a small enough set of users that someone can individually hunt us each down and help us, you know, do whatever magic is necessary to change the key. So the advantages of this model is that to build a PKI within your own organization, there's no need to pay any outside organization. Also, security within your own organization is entirely in your own hands. If you manage your own CAs well, it doesn't matter if all the other CAs in the world are compromised. What's presumably the most security sensitive stuff, which is authentication between users and resources in your own namespace, those paths don't go beyond your own organization. There's also no single compromise key that requires massive configuration, and it's kind of easy configuration because you could really start with just your own key. Okay, so now another thing I'll talk about is what layer should you do cryptography at? Layer 2 protects the link hop by hop, and it kind of makes, if you want to prevent traffic analysis, that way you can hide the IP headers so that someone can't see that Alice is talking to Bob. Layer 3 and 4 is like SSL or IPsec, and I'll talk more about that on the next slide, what the difference between Layer 3 and Layer 4 is, but it protects end-to-end real-time conversation. Whereas upper layer is another thing that you may want to do, like you may want to protect email with PGP or S-MIME, or you may want to protect kind of messages at the XML layer. So there's XML DSIG is the standard for signing data, and XML encryption is a way of encrypting data. And this allows you to protect data that's in place rather than during the conversation, which is what layer 3 and 4 is. Now, the term key exchange, I've always hated. To me, when you say key exchange, I think I'm agreeing to tell you my key if you tell me your key, but that's not what they mean. For some reason, the security community has given the term key exchange means that you and I do mutual authentication and agree on a secret key that we're going to protect our conversation with. So examples of these things are SSL or TLS, which is really kind of the same thing, and IPsec. So what's the difference? IPsec is layer 3, SSL is layer 4. So again, this is a nice short answer you can write on a quiz, but it doesn't really give you any intuition as to what the real difference is. So the real difference is that layer 3, the idea behind IPsec was let's not change the applications. Let's do security once in the operating system, and then automatically, without changing any of the applications, we will automatically protect all applications and make everything secure. The layer 4 idea was it was the opposite. They said let's not change the operating system. And so what's in the kernel is layer 4 and below. So they said we're going to be something that does cryptography on top of TCP. And so TCP and below, by definition, we're not changing them, so they don't know that any crypto is going on. So if you want to do SSL, you have to change your application so that instead of hooking into TCP, it hooks into SSL. So, okay, let's see, do I have I don't have a slide about that. So there's actually, layer 3 is actually technically superior in a way, because given that every single packet is individually protected, you could build, layer 4, by definition, TCP is not aware of the cryptography. So there's this problem that I call the rogue packet problem, which is that if somebody is observing you talking in an SSL session, they can inject a packet that will look okay to TCP, because there's no cryptography preventing me from doing that. And if I can get TCP to accept the next chunk of sequence number, then the real data won't be able to get through, because there's no way, even if SSL knew that was the problem, there's no way for it to tell TCP back up your sequence number. But so by sending a single message, you break the connection. There's nothing else that they can do to recover. Whereas IPsec, each packet is individually cryptographically protected, and so it would be immune from that attack. But unfortunately, I think I have slides on this, but I'll get to them later, so I'll talk about it now. If you don't change the API, though, there's a problem with IPsec, which is that IPsec does all this complicated PKI-based authentication that I can prove on radia.perlman.sun.com, but if you don't change the API to the application and don't change the application, the only thing IPsec can tell the application is you're talking to IP address 79. So although it encrypts the conversation, it doesn't tell the application who you really are. So what you would wind up having to do is do all this fancy, expensive public authentication, but then if the application cares who you really are, you have to type your name and password. So ideally what the world will migrate to is you know, a layer 3 approach, but also changing the API so that IPsec can tell the application who it actually authenticated. So AH and ESP is how IPsec works. It's kind of an, it shows the packet format for encrypting or integrity protecting a conversation. And so AH does only integrity, whereas ESP was originally designed to only do encryption. And so, but then ESP added optional integrity protection. And then the question is, why shouldn't we just use ESP? And basically, these two committees don't really like each other very much. The AH people are kind of the IPv6 zealots, and the ESP people are the security geeks. So the ESP people, you know, at first they said, hey, you know, it makes no sense to do encryption without integrity protection, so therefore we should add optional integrity protection. And the AH people weren't paying attention, because if they had, they would have said, if you need integrity protection, you have to use AH also. But they didn't. So ESP added optional integrity protection. And then ESP said, oh, you know, there's legitimate times when you only want integrity protection and you don't need encryption, at which point the AH people were paying attention. And so they said, no, no, that would violate the architecture. And this is like a great argument you can always use, you know, no matter what the question is. No, that would violate the architecture. So at this point, the ESP people came up with what is my absolute favorite RFC. They said, okay, we can't make encryption optional, but we can negotiate any encryption algorithm we want, right? So they invented a new encryption algorithm that they called null encryption. And they have this wonderful RFC talking about how wonderful this new algorithm is. It's very fast. It works with any key size. You don't even have to agree on the key. And then they have some test data to test your implementation against. So, yeah, basically, there's some sort of mutual authentication that goes on to allow you to establish a security association. What a security association is, it says what the key is, who you're talking to, what your sequence number is, what your cryptographic algorithms are, and so forth. But when you actually receive an encrypted message, how do you know which key to use to decrypt it? So there's this magic number that you put into the header known as the SPI, where once Alice and Bob negotiate to decide on a key, Alice says, if you want to talk to me, put the magic number X into your packets. And that will enable me to look in my own database and say, I handed X out to Bob, so I know that's who I'm talking to. And Bob says, use Y. So now when Alice sends an IPsec packet to Bob, she puts in Y. And when Bob sends it, puts in X. So here's what ESP looks like. You have the IP header, and there's a field that in IPv4 is known as protocol type, and the exact same field is known as next header in IPv6. And if you put 50 in there, that means that you have this ESP header. So if you had a TCP packet, it would have said 6 up there, but now you displace the 6 and put a 50 in there, and then at the end, you put in the 6 that you displaced. You put it in the end. And here you have this header that says what the SPI is and what the sequence number is, and the rest of it's encrypted. And then the integrity check is over the ESP header, and it basically starts from here and goes to the end. AH is similar, but you put 51 instead of 50. But this is supposed to look like an IPv6 extension header. Also, the integrity check, instead of just being AH and below like ESP is, they also integrity protect certain parts of the IP header. So they can't integrity protect the entire IP header because certain fields change, like the hop count. So therefore, AH unfortunately mucked up the IP spec because it made it much more complicated. For every spec, for every field, you have to say whether it's mutable or immutable. If it's immutable, it means that it can be covered by the integrity check, and if it's immutable, it won't be. And in case that wasn't complicated enough, somebody came up with some fields that were mutable but predictable. You could see what it was going to look like at the end. And so the integrity check here includes, you know, all the things that are immutable and mutable but predictable, and any other fields you have to zero out. So to be, well, I think I can be, even though I'm being recorded, I guess I'll tell this story because it's funny, even though it's horribly politically incorrect. I didn't even ask who's going to get to see that, but oh well. So, yeah, someone must put something in my Coke. Oh well. The ESP people have desperately tried to get rid of AH. And so, you know, like the reason the AH people want to protect certain of the IP header is that they really want to make network address translators stop working. Well, as it turns out, NATs, have a lot of trouble with this thing anyway. But so nobody has come up with any valid security reason why it matters to protect the IP header. Basically, if you receive a packet and it's cryptographically protected with the key that you share with somebody else, you know who it is you're talking to. It doesn't matter how the packet arrived to you. So there's no real reason to do that. But yeah, towards one of the last meetings before this was cast in concrete, someone from Microsoft got up and gave an impassioned talk about how he hated AH and wanted to get rid of it. He said, as an implementer, here the integrity check is right at the top as opposed to at the bottom for ESP. So you have to buffer the whole packet before being able to know what the integrity check is, either on incoming or outgoing. Furthermore, trying to do a chunk of memory and say, compute an integrity check on this, he can do. But if he has to like zero out certain fields, predict what other ones will be and so forth, it's real painful to have to do an integrity check on the IP header. And besides that, there's no real reason to do that. So, you know, my feeling at the end of that was that kind of everybody in the room looked around at each other and said, you know, he's right, but if it annoys Microsoft, let's leave it in. So what's going on in the IETF security area? Well, there's the Kerberos working group, which, you know, as somebody pointed out, is kind of getting more and more public key oriented to at least get rid of the database of secret keys. PKIX is a certificate format, which I'll talk a little bit about on the next slide. There's SMIME and PGP, which are ways of encrypting and integrity protecting data. SASL is a syntax for negotiating which authentication protocol you're going to use. DNSSEC is a way of adding public keys into DNS or signing the information that is in there, like the mapping between a name and an IP address. And then there's SACRED, which I included on this slide just because I love the name. It's secure credentials. So it's a way of obtaining a private, of having the user obtain their private key if they're not carrying it around on a smart card. Now, PKIX is based on X509 certificates. I've seen the IETF make so many like bad decisions because of not invented here. And so I was really quite surprised when they adopted X509 as the certificate format. Now, what's wrong? I mean, a certificate is just so simple. Why should you care who invented it? Well, it isn't like who invented it. There's two reasons why people don't like X509. One is that it's based on ASN1 encoding, which is just sort of this complex encoding that requires a big parser in your machine. So it's a big footprint. It's slow to parse these things and you know, kind of expensive. But that's just syntax. And, you know, I used to hate ASN1 until I saw XML. And but the real problem with X509, it's like, what were they thinking? What good is a certificate if the names in the certificate are not the names that your applications are using? So in X509 certificates, they had X500 names, which look like, you know, C equals US, whatever. It's a hierarchical thing, but it's a different string than a DNS name. And it's, you know, a different body that defines these names. So what do you do? So some browsers in the early days said, okay, the user type www.schwab.com, and the thing gives me this certificate with some string in it that there's no way for me to compare it with the user. So some of the browsers verified the signature but ignored the name, in which case you're getting no security at all other than the warm, fuzzy feeling that somebody paid VeriSign some money. So these days there's various, kludges to add a DNS name into there. So yeah, names are problematic no matter what. What if there's several John Smiths in an organization? Now, if all parents were as creative as mine were, we wouldn't have that problem. I really don't understand the people that know they're pregnant for they have 9 months, and then, at the end, you say, well, did you think of a name? Yes, I did. We finally got the name. Well, what is it? John. It took you that long for that, So yeah, there's a quote in the book about somebody said, why did you name your child John? Every Tom, Dick, and Harry is named John. So anyway, is PKI dead? That's something disturbing that I keep hearing people say, and it can become a self-fulfilling prophecy. So you try to sell something based on PKI, and your customer says, isn't PKI dead? I heard it was dead. No, it's not dead. We use it every day with SSL. Maybe what people mean is that we don't have user certificates, but this stuff shouldn't be that hard. So it's, kind of frustrating to me that the world has not really done single sign-on based on public keys. So how it ought to work is to take this wonderful slogan, the network is the computer. That, is Sun's slogan. I would like to think that we do it better than anybody else, but somebody once did a T-shirt run that I would love to have my hands on, one of them, that said, the network is the network, the computer is the computer, sorry for the confusion, Sun Microsystems. But, basically, what should happen is that when you create an account, the system administrator should say, here's a username and a password. The system should create a public-private key, certify the public key, encrypt the private key with the user's password, and then when the user types a name and password, somehow it activates their private key, and they authenticate it to everything with the public key. Novell's system worked very similar to this, and that was many, many years ago. So, okay, here's the last slide, which is a quote that my co-author said at a talk once that I just think says it all. Until a few years ago, you could connect to the internet and be in contact with hundreds of millions of other nodes without giving even a thought to security. The internet in the 90s was like sex in the 60s. It was great while it lasted, but it was inherently unhealthy and was destined to end badly. I'm just glad I didn't miss out this time. So thank you, that's it.